Hello, my name is Ghazal Zand. I'm a PhD student and a member of Inclusive Interaction Lab at University of California, Merced. Today, I will present our work, TeleDriver, a driving simulator-inspired technique for steering telepresence robots. Telepresence robots are becoming increasingly popular for remote communication and exploration. There are a variety of commercial telepresence robots available. We used Omni Telepresence robot in this project. A challenge in interacting with telepresence robots is difficulty in operating them effectively. Users often find tasks such as adjusting and maintaining speed, turning and reversing the robot boring and cognitively demanding, leading to navigational errors in crowded environments like hospitals. We developed TeleDriver, a desktop platform to control telepresence robots using a driving simulator that could be set up at home or in shared spaces. We decided to exploit the existing driving skills of users by allowing them to control telepresence robots using a driving simulator equipped with a steering wheel, pedals, and gear shifter. We also wanted to explore the possibility of users embodying a telepresence robot just like they embody the car while driving. The complete setup can be seen here. In TeleDriver, the rotation of the steering wheel is mapped to the rotation of the robot using a linear function. The shifter is used to switch between forward and reverse motion. The speed of the robot is controlled by gas and brake pedals using a different linear function. We conducted a study with two groups of users, 12 drivers and 12 non-drivers, to compare TeleDriver and OmniRobot's default app. Participants used both methods in counterbalanced order and had 4 trials for each method. We logged speed and accuracy. We also used system usability scale for evaluating user perception of each method and NASA TLX questionnaire to evaluate user perceived workload. An additional goal was to see if drivers could apply their driving skills to TeleDriver. They were asked to maneuver the robot through an obstacle course and return it to the start, ensuring all robot control functions were utilized. The average task completion times with the default method and TeleDriver in overall were the same. But when we split the data for drivers and non-drivers, we can clearly see that drivers performed better. Results show that drivers using TeleDriver were 23% faster, but non-drivers using TeleDriver were 26% slower compared to the default method. Although non-drivers performed better with default method than TeleDriver, we can see that their performance improved over time. By last trial, non-drivers were 13% and drivers 17% faster than their initial attempts using TeleDriver. Overall, users made more errors using TeleDriver compared to default method, most probably because they were still learning the system. In the second graph, we can see that non-drivers had more errors using TeleDriver, but drivers were more accurate with it. According to the results, drivers using TeleDriver made 39% fewer errors, while non-drivers using TeleDriver made 147% more errors compared to the default method. The performance of both user groups was similar when using the default method. Again, although non-drivers made less errors with the default method than TeleDriver, we can see that their error rate decreased over time. In the last trial, non-drivers experienced a 63% decrease in errors and drivers saw a 58% reduction in error rates versus the first trial. Drivers perceived TeleDriver to be significantly faster than the default method. They also enjoyed using TeleDriver significantly more than the default method. They felt that both methods were similar in terms of learnability and ease of use, so were confident in using both. Non-drivers, in contrast, found TeleDriver to be significantly more difficult to learn and use, thus were not as confident in using it as the default method. Non-drivers rated TeleDriver more difficult to learn, most probably because they had no experience with driving. Non-drivers did not perceive the methods to be significantly different in terms of speed and accuracy, and they enjoyed using both methods. Drivers learning well and feeling more confident using TeleDriver suggests that the embodiment mentioned earlier, where drivers would be able to embody the operation of telepresence robots as they do with cars, most probably had happened. In terms of perceived workload, drivers perceive TeleDriver to be significantly better performed and less frustrating than the default method. They found both methods to be not as demanding and somewhat comparable in terms of mental, physical, and temporal demands and effort. Non-drivers, on the other hand, found TeleDriver to be significantly more demanding in terms of mental, physical, and temporal demands. They felt that it required significantly more effort to use, not as well performed as the default method, thus causing significantly more frustration during the study. These results show that TeleDriver enabled skill transfer. Drivers were able to transfer their driving skills to driving simulator operating telepresence robot. The results also show that both drivers and non-drivers were learning the method over time. While drivers initially performed better, we suggest that with more experience using the system, non-drivers' performance could reach a similar level. According to the results, TeleDriver is an effective method for operating telepresence robots for both drivers and non-drivers. A limitation of this study is a small and relatively young sample size, primarily due to challenges in recruiting adults with no driving experience. In the future, we will extend the work for a better enhanced sense of embodiment by providing information on the robot's ambient environment using haptic feedback. Thank you.